This is question number 1. It says calculate the sum of 66.8 kilograms and 3,685 grams in milligrams. Okay, so our first step is going to be write down what is given, and we're going to think about the problem and draw any diagrams if necessary. And so this is a pretty simple problem, so we don't really have to draw any diagrams. So we write down our knowns. We're given that the first quantity is going to be 66.8 kilograms, and our second quantity is going to be 3,685 grams. So we're going to see that the problem is asking us to calculate the sum in milligrams. And so what we need to do is we're going to have to convert these two masses in terms of milligrams. So if we do that, we're going to write down the necessary equations or conversion factors. If we can see here, for our 66.8 kilograms, we can see that the conversion factor is given right there. If we multiply our 66.8 kilograms by 1 million milligrams per 1 kilogram, this is how many milligrams it should be. And just to write this out so it's clear, 66.8 kilograms, and we know that in 1 kilogram there's going to be 1 million milligrams, and so the kilogram unit cancels out, and so we're left with the unit of milligrams that we want, and that's how we got the 66,800,000 milligrams. We do the same thing for 3,685. We see that this is the conversion factor. For every 1 gram, we're going to have 1,000 milligrams. And if we multiply 3,685 by that conversion factor, we're going to get 3,685,000 milligrams. And then lastly, we just go ahead and solve the problem. It's asking us to calculate the sum. So now that we've converted both of these into milligrams, we can just go ahead and add them. And if we add them, we get 70,485,000 milligrams, and that's given right here. And if we look at our answer choices, we can see that all of them are in scientific notation. And so if we convert our number to scientific notation, we should get 7.05 times 10 to the 7th. Notice that the 8 is going to round up and make the 4 into a 5, and that's where we get the 7.05. And so if we look at our answer choices, we can see that that's going to be answer choice D as our correct answer. This is question number 2. It says a car travels 55 meters north. It turns 60 degrees to the right and travels 45 meters. And we're asked, how far is the car from the initial position? Okay, so step 1, we're going to go ahead and write down what we're given. And we're going to try to think about the problem and whether or not it's necessary to draw out the picture if we need to. Okay, so what we're given is that this car is going to be moving 55 meters north, and then it turns 60 degrees to the right, and then it travels another 45 meters. Okay, so if we were to kind of draw this out as a diagram, we can see that the car moves first 55 meters north, shown by the blue arrow, and we're supposed to then move 60 degrees to the right. Now that's kind of hard to imagine, so if we draw an XY coordinate plane, we can kind of see it more easily. So if we do 60 degrees to the right, we can see that that would be something like that. And we can see that the amount that is traveled is 45 meters, and it's going to be given by the green arrow. Okay, so that's the distance in which the car has traveled. Now what we're trying to find is, we're trying to find what the amount is from the initial position, which is right here, and the final position, which is right here. So we can see that the blue arrow right here is purely made of just the y component, so we're fine. Whereas the green amount traveled, or given by the green arrow, is made of both y and x components. So in order to solve for these, we're going to have to use trigonometry. If we go ahead and draw a horizontal dotted line, we can see that we can calculate the distances as components by using trigonometry, and we're given the angle of 60 degrees right here. Okay, so let's go ahead and write down what we need, what equations we need. So like we stated earlier, our blue arrow is traveling north, so there is no x component. If we're saying the x component is east and west, the car initially does not move anywhere east or west. It only travels north, and so all of the distance traveled is going to be in the north direction, or the y component. Next, the car turns right 60 degrees and then travels 45 meters. So for the x component, in order to find the x component, that's going to be the distance right here. And in order to find out the x component, we're going to have to take the distance traveled times the opposite, which is right here, of the angle of 60 degrees. So that would be 45 times sine of 60. And that would give us approximately 38.971 meters. To find the y component, which is going to be this distance right here, we take 45 and we are going to multiply it by the cosine of 60. And that comes out to 22.5 meters. Now, in order to figure out the distance, we're going to have to use the Pythagorean theorem, in which we're going to add all the x components together, square it, add all the y components together and square it, and that's going to equal the distance squared. And we can find the distance by taking the square root of that, and that's given right here. So remember, square root can also be expressed as something to the 1/2 power. Okay, so let's go ahead and do that, plug all our values in. So for our total x component, we're going to take all the x components of the blue distance that we traveled, which we had established that there was no x component, so that's 0. From the green arrow, we know that's going to be 38.971. So our total x component is going to be 38.971. For our total y component, we're going to add the y component of the blue arrow, which was 55. We're going to add the y component of the green arrow, which we calculate to be 22.5. And when we add them together, we're going to get 77.5. And we use those x component and y components to plug it into our Pythagorean theorem and solve for the distance. And if we do that, we should get around 87 meters. And if we look at our answer choices, that's going to be answer choice A as our correct answer. This is question number 3. It says, find the resultant force from the 3 forces shown in the figure. Okay, so let's go ahead and write down what we know and think about this. Since we're already given a figure, we don't have to draw anything. Let's just examine it. So we're asked to look at our 3 forces and calculate what the resultant forces are going to be. So in order to do that, we're going to have to add these forces together. And the only way we're going to be able to add these forces together is to break them up into their component parts. Okay? So if we look at our 40 Newton force right here, we can see that it's only in the x direction, and so there's only x component to it. And if we look at our 60 Newton force, what we can see is that it's only in the y direction, and so it only has the y component. Now if we take a look at our 80 Newton force, we can see that there's some x component and y component. So this right here is going to be the x component part, and then this right here is going to be our y component part. So let's go ahead and do the equations in which will let us break these and organize these components of the forces. So again, if we look at our 40 Newton force, we know it's only in the x component direction, and it's going to the left, and so that's why there's going to be a negative. There's no y component, and so that's going to be 0. If we look at our 60 Newton force, there's no x component, so that's the 0. In the y component, it's all in the y component, and it's in the up direction, and so it's going to be positive, so that's 60. If we look at our 80 Newton force, it's going to be made up of the x component and y component. In order to figure out the x component, we're going to use 80 times the cosine of 30. Of course, 30 is going to be the angle, and if we do that, if we do the equation, we do the calculations, we can see that the x component is going to come out to 69.282, while the y component, we know that's going to be 80 times sine of the angle 30. It's going to give us negative 40, and that makes sense because it's going to be below the y-axis right here. And so now that we have broken up and organized all our forces into components, we can then figure out the resultant force by using Pythagorean theorem. We can also use the inverse tan to figure out the angle at which it's at, or the direction. If we look back at Pythagorean theorem, we know that x squared plus y squared is going to give us the hypotenuse d squared, and what we want to find is we want to find the resultant d, and to do that we're just going to take the square root of it. And just to note, bringing something to the 1/2 power is the same thing as taking the square root of it. So just to clarify so there's no confusion. Okay, finally step 3, we're going to solve it by plugging all our values in. So let's just focus on the x component first. We're going to plug in all our x component values. So that's going to be negative 40 from the 40 Newton force, 0 from our 60 Newton force, 69.282 from our 80 Newton force, and that's going to total out to become 29.282. We now focus on the y component of each force. For the 40 Newton force, there's 0. For the 60 Newton force, it's all in the y component, so that's going to be 60. For our 80 Newton force, it's going to be negative 40, and that's going to come out to a total of 20. So then now that we have our values for the x component and our value for the y components, we're just going to plug it in to find the resultant force. We do that, the calculations come out to be 35.5 newtons. And if we look at our answer choices, we can see answer choice A has 35.5. It also adds in the direction. So let's go ahead and find the angle. And we know that the angle can be found by taking the y component over the x component, taking the inverse tan. If we do that, we're going to get 34.3. And again, that verifies that answer choice A is going to be the correct answer. This is question number 4. It says, starting at rest, you run 60 meters while running faster at a constant acceleration. How long did it take you to run this distance if at the end of your run, your speed is 9 meters per second? Okay, so let's first write down what we're given. We're told that the run is going to be 60 meters. We know that the acceleration is constant, but we're not given the acceleration. We're told that we're initially at rest, and so our velocity is going to be at 0 meters per second. And at the end of the run, we know that our final velocity is going to be 9 meters per second. And finally, we're asked how long this took. So let's kind of imagine this in a drawing. So at first, we're at rest. And so we know that our velocity, our initial velocity, is going to be 0 meters per second. And we're going to run 60 meters. And at the end of that 60 meters, our velocity is going to be 9 meters per second. So if we can imagine this, we can kind of get an idea of what equations we need to use. If we're initially at rest and we run a certain distance and we have a final velocity and we can figure out, we're told that we have a constant acceleration and we need to figure out the time, we can use the velocity, final velocity is equal to initial velocity plus the acceleration times time equation. However, we don't know the acceleration and we don't know the amount of time. So there's another equation that we can use, and that's going to be our final velocity squared is going to equal the initial velocity squared plus 2 times the acceleration times the displacement. So now that we only have one unknown, and that's going to be our acceleration, we can go ahead and solve for it. And if we solve for it by plugging all of our values in, our final velocity is 9, so it's 9 squared. Our initial velocity is 0, so it's 0 squared. We add 2 times the acceleration. We don't know the acceleration, so we just go ahead and put 2a. And we know that the displacement is going to be 60 meters, so that's where the 60 meter comes in. If we do that and we can solve for the acceleration, it comes out to 0.675 meters per second squared. Now that we have the acceleration, we can plug that in to our first equation to figure out the time. If we do that, we can plug in our final velocity again as 9, our initial velocity is 0, our acceleration is what we just found, 0.675, and we can solve for time, and that should be 13.3 seconds. If we look at our answer choices, we can see that that's going to be answer choice C as our correct answer. This is question number 5. It says you are at rest on your bike. You hear a start signal and constantly accelerate for 3 seconds at 1 meters per second squared until you get tired and cruise at this velocity for the next 5 seconds. And we're asked, how far did you travel during this time? So let's go ahead and write down our givens. We know that we're asked to figure out how far we traveled, and so that's going to be represented by x. We know we accelerated for 1 meters per second squared for 3 seconds. We know that we started at rest, and so our initial velocity is going to be 0 meters per second. And we know after the 3 seconds of acceleration, we now have a final velocity, and we cruised at that final velocity for 5 seconds. Okay, so let's kind of illustrate this in a picture. So initially we're at rest, and that's going to be shown right here, in which our initial velocity is 0 meters per second. And when we hear the start signal, we're going to start accelerating at 1 meters per second squared for 3 seconds. And after 3 seconds, we get tired, so we stop accelerating. So we can kind of divide this problem into 2 parts. So after 3 seconds of accelerating, we're at some speed, but we decided not to accelerate anymore because we're tired, and so we're cruising along at whatever speed that is for the next 5 seconds. And so that's shown right here. And it's asking us, what is the distance during this whole time? Okay? So there is a displacement equation that we know. That's going to be x is equal to x initial x naught plus initial velocity times time plus 1/2 at squared. And we also have a equation in which it accounts for acceleration and the amount of time. And so that's shown here. And so if we kind of divide this problem into two parts, let's say that this is going to be our part 1, in which we're just accelerating, and this is our part 2, in which we're just cruising. We can go ahead and try to solve it that way. So during acceleration, which is part 1, so let's say this is part 1. During acceleration, the distance we travel is going to be the distance at which we're originally at, times the initial velocity times time, plus 1/2 times the acceleration times time squared. So for the initial position, we're starting at the exact position, and so we're going to say that that's going to be at 0. So that's represented right here. We're at rest, and so our initial velocity is 0, and we're going to multiply that by the time. And so our velocity is 0, so our time doesn't really matter. It's just going to be 0 since it's multiplied by 0. And then we have the acceleration component, which is going to be 1/2 times the acceleration, which we know is going to be at 1 meters per second squared, and we accelerate for 3 seconds, and so that's going to be squared. If we do the math, that's going to come out to be 4.5 meters. Okay, so that's part 1 in terms of how far we traveled. Now for part 2, we need to figure out the cruising velocity in which we continue on for 5 seconds. Now we can figure out the cruising velocity by the equation of final velocity is equal to initial velocity times acceleration times time. So remember, our initial velocity was 0, and we accelerate at 1 meters per second squared for 3 seconds. And so our final velocity, at the cruising velocity rather, is going to be 3 meters per second. And so we can use that for part 2. So this is during cruising, and we can label that as part 2. So the distance we traveled while we were cruising is going to take into account the position that we initially were at, plus the velocity, initial velocity, times the time, plus 1/2 the acceleration times t squared, or time squared. And that's going to give us the distance we traveled. Okay? So now our initial velocity, or initial position rather, is going to be at the 4.5 meters we had traveled during acceleration part. Our initial velocity is going to be the velocity at the end of our acceleration part. So that's going to be right here, the 3 meters per second. And we're cruising at this velocity for 5 seconds. Then we're going to add the acceleration component, which is 1/2 times the acceleration. Remember that we're too tired to accelerate anymore, and so our acceleration is just 0. And we're doing this for 5 seconds, so it's just 5 squared. We do the calculations, it comes out as 19.5 meters. And if we look at our answer choices, we can see that none of our answer choices has 19.5 meters, and so we choose answer choice E, none of the above, as the correct answer choice. This is question number 6. It says some hotshot executives decide to play golf on the roof of a building that is 90 meters tall. One of the executives throws the ball straight into the air with an initial velocity of 36.2 meters per second and lets it fall to the ground below the building. How many seconds does this take? Okay, so let's go ahead and first write down what we know. We know that the ball is going to be on top of a building that is 90 meters above the ground. We know that we're going to be dealing with gravity, and since the gravity is going to be in the opposite direction of the ball being thrown, it's going to be negative 9.81 meters per second. We're told that the ball was thrown with an initial velocity of 36.2 meters per second, and we're trying to figure out the time in which it took for the ball to travel to the ground below the building. So let's try to illustrate this with a picture. We can see that at first the ball is going to be on top of the building that is 90 meters tall. It's going to travel up until some point in which gravity is going to stop the ball and make the ball then start falling down toward the ground. And so then it travels downward toward the ground until it finally hits the ground, and we're trying to figure out how much time this all took. So we can say that the green arrow can represent the amount of time it took for gravity to cancel out the initial velocity, and this is going to be the point in which the ball is going to be at its maximum height. And from its maximum height, we can then figure out the amount of time in which it took to be from the maximum height to fall all the way to the ground. So we can say that this is going to be the time it took to fall from its maximum height to the ground. So let's say that's T2. And then let's say the other one is going to be T1. And if we add T1 and T2 together, we're going to get the total amount of time it took. So we know that there's an equation in which it takes into account velocity and acceleration. And to figure out the time it took to cancel out our initial velocity, we can say that the final velocity is equal to the initial velocity plus the acceleration times time. And we're trying to figure out the time. We know that when the ball is thrown up in the air with initial velocity of 36.2, we can plug in here, and it keeps traveling up until gravity is able to cancel out the initial velocity. So then the final velocity will then have a velocity of 0. At that point, that's where it's going to be at its maximum height. So we have all our variables, and so we can solve for the t, or the time. If we do that, it's going to come out to 3.69 seconds. So that's going to be our T1. We can use that T1 to figure out our maximum height. Remember, our displacement equation can be rewritten with the variables that we need. In this case, instead of x, we're going to put in h, because we're dealing with height. We can also use y if we want, but whichever one is going to be easiest to remember. So we're trying to figure out the maximum height that the ball is at, and so we can use that maximum height to then calculate the amount of time it took to fall from that maximum height down to the ground below. So the next step is to find the maximum height. And so we use this equation right here, in which the maximum height is going to equal the initial height plus the initial velocity times time plus 1/2 the acceleration times time squared. So if we do that, we know that the initial height is on top of the building, which is 90 meters. We know that the initial velocity is 36.2, and we just calculated the number of seconds that it traveled at that speed. And we know that the acceleration is going to be due to gravity, and it's going to be the opposite direction of the velocity, and so we have negative 9.81. And again, we use the same amount of time in which it was acted upon. If we do the calculations, we can see that the maximum height is going to equal 156.791 meters. Now that we have the maximum height, we can figure out how long it took to fall at that height to the ground below. And we know that the equation that we can use is that the maximum height, or just height in general, is equal to 1/2 times gravity times the amount of time squared. If we rearrange the question, or rather the equation, we can find out what the time was. And what we get is the square root of 2 times the height divided by gravity. If we plug in our values, we should get the time it took to fall from the maximum height down to the ground below as 5.654 seconds, shown right there. Now that we have our time 1 and our time 2, we just add them together to solve the question. And what we should get is 9.344 seconds. If we look at our answer choices, we can see that answer choice C is going to be our correct answer. This is question number 7. It says, for 2 identical potatoes, you drop it like it's hot. For potato 1, the height was h, and 2h for potato 2. How much time would it take for potato 2 to drop to the ground if it takes potato 1 time t? So let's first write down what we're given. We're told that the height for potato 1 is at h, and the height for potato 2 is twice that, so it's going to be 2h. And we're dealing with gravity, and we know that the acceleration of gravity is 9.81 meters per second squared, and that the time for potato 1 that it takes to hit the ground is going to be t. So let's write down the equations that we know we're going to use. We know that to solve for the time, for free fall, it's going to equal the square root of 2 times the height divided by gravity, and that's given right here. Now, let's go ahead and try to solve these. The most straightforward method is probably just to assume some easy numbers that you can calculate. So that's what we're going to do. We're going to let the height of potato 2 equal 10 meters. If we do that, and we calculate the time it takes for that potato to fall down 10 meters, we're going to get 1.428 seconds, and that's given right here. And since we know that the height for potato 2 is going to be twice that of potato 1, we just multiply it by 2 to get 20 meters. We plug that into the equation, and we get the time it takes for potato 2 to fall to the ground. And that's going to be 2.019 seconds. Now, if we're able to compare these two by dividing them, or getting the ratio of potato 2 to potato 1, as is asked in the question, what we're going to get is it's going to take potato 2 1.414 times as long to fall to the ground. So if we look at our answer choices, we can go one by one to see which one matches up with that ratio. So for answer choice A, it says 2.5 of the time of potato 1, so that's not right, so we can eliminate that answer choice. For answer choice B, it's 3/2 or 1.5. That's close, but not quite. For answer choice C, it says t divided by 2, or 1/2 t, which is the same thing as 0.5 t, which is not correct, so we can eliminate that answer choice. For answer choice D, it says 2 to the 1/2 power, which is the same thing as the square root of 2, and that is going to equal approximately 1.414. And so answer choice D is going to be our correct answer. This is question number 8. It says a ball is thrown 30 degrees above the horizontal with initial velocity of 2.15 meters per second. How long does it take before the ball stops rising? Let's first write out what we're given. We know that the ball is thrown up at an angle of 30 degrees above the horizontal. And so we know that gravity is going to be involved. And since gravity is going to be acting on the opposite direction of the velocity, we're going to give it a negative 9.81 meters per second squared. We're also told that the initial velocity is 2.15 meters per second, and it's being thrown at an angle 30 degrees above the horizontal. And we're trying to find the time in which the ball is no longer moving. We're no longer increasing in height or rising. And so we're specifically trying to find the velocity in the y component, in which it's 0 meters per second. So let's try to draw out a picture to better see what's going on. So imagine we have a ball and we're throwing it above the horizontal at an angle of 30 degrees, and its initial velocity is going to be 2.15 meters per second. And so the type of problem we have here is projectile motion. And what we know about projectile motion is that it's going to mirror a parabola, in which the ball is going to keep rising and rising until at some point gravity is able to counteract the velocity in the y direction, and then it no longer has any velocity in the y direction, and so it falls down toward the ground. And at this point right here, we know that that's going to be the maximum height. We also know that that's going to be the point in which we're going to have the velocity, specifically the velocity in the y direction, equal to 0 meters per second. Okay, so let's write down the equations that we're going to use. We know that we're trying to find the time in which it takes to cancel out the initial velocity. And this is going to be the same point in which the ball is at its max height. So it would make sense to use the equation in which the final velocity is going to equal the initial velocity plus the acceleration times time. But we're only going to be interested in the y component. And so we're going to modify our equation to specify that it's going to be just in the y component. So our initial velocity is going to be in the y direction, and that's going to be equal to the initial velocity times sine theta. And so instead of just the initial velocity, we're going to use the velocity sine theta. And that's what we get here. And we are going to specify that since it's projectile motion, the acceleration is going to be gravity. And so we put in g. Now if we do that, we can plug in our numbers, and we get something like this, in which the final velocity in the y direction is going to be 0 because it's no longer moving upward. This is our initial velocity in the y direction. So it's 2.15 sine of 30 degrees, which is this. And then we're going to add acceleration times time. Now we know acceleration in this particular problem is going to be gravity, and it's going to be in the opposite direction of our velocity, so we give it a negative 9.81. And we're trying to figure out time. And if we solve for time, what we're going to get is time is equal to 0.110 seconds. And if we look at our answer choices, we can see that answer choice C is going to be our correct answer. This is question number 9. It says a parachuter sees a spot he wants to land 182 meters directly beneath the plane he is on. The plane is flying parallel to the ground at 72.6 meters per second. If the parachuter jumps out of the plane and his downward acceleration is 5.82 meters per second squared, how far will he land from the spot he wants to land? Okay, so let's first write out what we're given. We're given that the height in which the plane is at and the spot he wants to land is going to be 182 meters. We're given that the plane is traveling parallel to the ground, so it's in the x direction. It's given as 72.6 meters per second. We're also given that the acceleration that the parachuter experiences when he jumps out of the plane is 5.82 meters per second squared. And we're trying to figure out how far he lands away from the actual point he wants to land. So let's go ahead and draw out a picture to better see what's going on. So let's say that the plane and the man is represented by the blue oval. And the spot he wants to land is going to be represented by the red rectangle. So the height between the spot he wants to land and the plane is going to be 182 meters. Now, we're told that the plane is traveling parallel to the ground at 72.6 meters per second. And so that's completely in the x direction. And so if the man jumps out now, he's going to travel some distance x and land here instead of where he actually wants to land. Now, to figure out the distance away from where he wants to land, we're going to have to first figure out how much time he spends in the air. And to do that, we need to calculate how much time it takes for him when he jumps out of the plane to actually reach the ground. If we figure out that amount of time, we can then use the velocity in the x direction to multiply that amount of time to figure out how far he is away from the spot he wants to land. So that's going to be our strategy. So let's go ahead and write down the necessary equations we need. So of course, we're going to be dealing with the displacement equation, specifically in the x direction. And we're going to be dealing with also the height. Since we're not dealing with gravity, since he has a parachute, it's just going to be the acceleration that's given. And if we rearrange this equation, we can figure out the time to take to cover the distance of 182 meters in height. We rearrange the equation, and our time t should be given by the square root of 2 times the height divided by the acceleration. So let's go ahead and plug in our numbers and try to solve for this. If we go ahead and plug in our height of 182, multiply it by 2, and divide it by the acceleration given as 5.82, we're going to get 7.908 seconds. And so that's the amount of time he stays in the air before he hits the ground. So that amount of time we can then use to plug in to our displacement in the x direction. And if we do that, we're going to get this right here, in which the initial displacement is 0, and the velocity in the x direction is 72.6, because that's the velocity at which the plane is moving, and so that's what he's going to experience when he jumps out of the plane. He's going to have that same velocity, and that's going to last for 7.908 seconds, because that's the amount of time he's going to spend in the air, and that's the amount of time we just figured out. And then we just add in the acceleration component, but since it's in the x direction, we know acceleration is just 0 in the x component direction, and so this term actually just cancels out. All we have to do is do the calculations, and we should get 574 meters away from the spot he actually wants to land. So this is going to be that distance. And so if we look at our answer choices, we can see that answer choice D is going to be our correct answer. This is question number 10. It says, in the physics building at a university, there is a scale on the elevator. A student who is trying to lose weight gets on the scale while the elevator is accelerating constantly downward. What does this student see? Okay, so since we're not really given any values, let's go ahead and try to draw a picture to see what's going on. So we would usually see the force of gravity, and that's going to be seen as our weight, and it's going to be mirrored by the normal force. But in this particular situation, we're on an elevator that's accelerating downward. So that's kind of the picture that we can draw. Now let's write down the equations that we're going to use. Okay, so we know that the force, or the normal force, is going to equal the force of gravity, which is going to be our weight, and that's going to be mass times gravity. But in this particular case, we know that there's an acceleration downward. And so the normal force and the force due to gravity are going to be different, and they're not going to be equal to each other. We can then write the equation of the normal force is going to equal to the force due to gravity, or weight, minus the amount in which the acceleration that we're experiencing. And so if we are to put the force due to gravity as mg, rather here, minus ma, that should equal the normal force. And since they have the same masses, we can factor that outside, and we can see that it's going to be the acceleration due to gravity minus the acceleration of the elevator times the mass, and that's going to equal the normal force. And since that's going to be less than the regular mg, we know that the amount that we see on the scale is going to be less than the actual weight of the student. And so if we look at our answer choices, we can see that the correct answer choice is going to be A. This is question number 11. It says, at the UPS boxing facility, a 5.1 kilogram box slides horizontally across a frictionless surface at 1.7 meters per second. If a 3.97 Newton force is applied to the box in the opposite direction, how many seconds does it take before the box stops completely? So let's go ahead and write down what we're given. So we know that the initial velocity of the box is 1.75 meters per second, and we're trying to figure out how long it takes for the box to stop. And so the final velocity of the box is going to be 0. We're told that the mass of the box is 5.1 kilograms, and the force that we're using to stop the box is going to be 3.97 newtons. So let's use this information to draw out a picture. So here we have our box, and it's sliding in the right direction at 1.75 meters per second. And that's going to be our initial velocity. Now, there is a force that's applied in the opposite direction, and it's going to be 3.97 newtons. And we're asked how long it's going to take before the box stops, and therefore the velocity, the final velocity, is equal to 0. So let's go ahead and write down the equation in which we need to use. We know that we're dealing with a force, and so we use the equation of force is equal to mass times acceleration, and we know we have a velocity influenced by acceleration. So we know we are going to use the final velocity is equal to initial velocity plus acceleration times time. Okay, so let's go ahead and look at these equations and how might they be used. We want to figure out the time variable, but we don't know what the acceleration is that's going to influence the velocity of the box. So we can use the F is equal to ma equation to figure out what the acceleration is from that 3.97 Newton force that we're applying. So let's go ahead and do that and solve this question. So if we use F is equal to ma, we can figure out the acceleration of the force that we're using by dividing the force by the mass. So we have the force as 3.97, the mass of the box is 5.1, and so we're applying a 0.7784 acceleration in the opposite direction of the velocity. And so that's going to be indicated by the negative sign. Now that we have the acceleration, we can plug it into the velocity equation. And doing so, we can say that the final velocity that we're trying to find which is going to be 0 since it's stopped, is equal to the initial velocity, which is 1.75, and it's going to be influenced by the acceleration from the force. The acceleration we found previously is negative 0.7784, since it's the opposite direction of the velocity, and times time, so we can solve for the time. If we do that, we're going to find out that the time is going to be 2.25 seconds, and if we look at our answer choices, the correct answer should be answer choice E. This is question number 12. It says, you have a mass of 7 kilograms with a 10 Newton force on it toward the eastward direction. What force would you need to bring the acceleration of this mass to 1 meters per second squared in the eastward direction? Okay, so let's write down what we have. We're told that we have a mass of 7 kilograms and that there's a force that's being applied to it of 10 newtons in the eastward direction. And in the end, we want this box, or this mass rather, to just have an acceleration of 1 meters per second squared. So let's draw out a picture to see what's going on. Okay, so here's our mass of 7 kilograms, and here's the 10 Newton force in the eastward direction. Now, what we really want is we're going to want the acceleration to only be 1 meter per second squared. And so we're asked what force is necessary in order to do that. Okay, so let's write down the equations that we need. Of course, we're going to need the force is equal to ma equation, in which force is equal to the mass times acceleration. Now, to figure out how we get the box or the mass to be accelerating at 1 meters per second squared, we need to first figure out how much the mass is accelerating using the 10 Newton force in the first hand. So if we do that, what we're going to do is we're going to solve for the acceleration by rearranging the force is equal to mass times acceleration by dividing the force of 10 newtons by the mass of 7 kilograms to figure out what it's actually accelerating right now. And we find that's going to be 1.429. However, we want it to be at 1 meter per second squared. So we have too much acceleration. So we know that our force that we need to apply is going to be in the opposite direction in order to slow that acceleration down. Now, to figure out how much force we need, we're going to have to figure out the difference of what we have and what we want. So if we take the difference of the acceleration of 1.423, which it's currently experiencing, and we subtract the acceleration that we need, we get the acceleration of 0.429. And that's the acceleration in which we need to apply a force to bring the acceleration down to 1 meter per second squared. So if we use the force is equal to mass times acceleration equation again, we use the mass, which is 7 kilograms, the acceleration that we need, which is 0.429, and we find that we need a 3 Newton force in the opposite direction of the 10 Newton force in order to slow down the acceleration to 1 meter per second squared. If we look at our answer choices, we can go ahead and eliminate answer choice B and C. Between answer choices A, we have 3 newtons in the westward direction, so that seems like the right answer. But let's go ahead and look at answer choice D. It says 3 newtons in the northward direction, so that doesn't make sense, and we can go ahead and eliminate it. So looking at our answer choices, we can see that answer choice A is going to be our correct answer. This is question number 13. It says, on the International Space Station, John and Gus are fighting over a corned beef sandwich and push each other. John weighs 0.8 times as much as Gus, and Gus accelerates 3.1 meters per second squared. What is the acceleration of John? So let's write down what we're given. we can say that the mass of Gus is going to be m. And if Gus's mass is m, then the mass that John has is going to be 0.8 times m. And the acceleration that Gus experiences is given as 3.1 meters per second squared. So let's write down the equation that we need to use. And that's going to be force is equal to mass times acceleration. Now, let's try to solve this. The most intuitive way probably to solve this is to go ahead and give actual numbers to m. So for this problem, I just went ahead and used 200 kilograms for Gus. And if John is 0.8 times Gus's weight, then his mass also should be 0.8. So then his mass is 160 kilograms. And we know from Newton's third law that for every action, there's an equal but opposite action. Then we can set the force of John equal to the force of Gus. And when we do that, we can fill in the equation in that, since we know that force is equal to mass times acceleration. And we know the mass of John is going to be 160 from our assumption. And the mass of Gus is going to be 200. And since we're given that the acceleration that Gus has is 3.1, we can then solve for the acceleration that John has. And if we do that, we're going to find that John's acceleration is 3.875 meters per second squared. If we look at our answer choices, that's going to be answer choice B as our correct answer. This is question number 14. It says you just bought a new car and are very nervous driving it for the first time. So you're going at 44.74 miles per hour in a 70 mile per hour speed limit freeway, straight north. You see bumper to bumper traffic and hit your brakes to come to a rest uniformly in 200 meters. What was the net force of your brakes if the mass of the car is 1,000 kilograms? So let's write down what we're given. We're told that you're initially traveling at 20 meters per second, and it takes you 200 meters to come to a complete stop. And so since you're at a complete stop, your final velocity is going to be 0 meters per second. You're also told that the mass of your car is 1,000 kilograms. So let's draw a picture to see what's going on. So your car is right here, and you're initially going at 20 meters per second. And then you see bumper to bumper traffic, you hit your brakes, and it takes you 200 meters to come to a complete stop. So your final velocity is 0 meters per second. We're also told that the mass of your vehicle is going to be 1,000 kilograms. So let's write down the equations that we need. We know that we need to find the force of the brakes, which is just going to be the mass times the acceleration. Then mass we know is going to be the mass of the car. However, we don't know the acceleration, but we can figure out the acceleration by the equation of v squared, which is just the final velocity squared, times the initial velocity squared, plus 2 times the acceleration times the displacement. If we do that to figure out the acceleration, what we're going to get is our final velocity, of course, is 0 since it's a complete stop. The initial velocity is going to be 20. And we're going to add that to 2 times the acceleration times the displacement. And when we do that, we can solve for the acceleration. And we find that the acceleration is going to be 1 meter per second squared. Now that we've figured out the acceleration, we can plug it into F is equal to ma equation to figure out the force. If we do that, we know the mass is going to be 1,000 kilograms. The acceleration we just found out was 1 meter per second squared. And so it will be 1,000 newtons. Now we know that we're going in the northward direction. So the brakes have to be applied in a force that is opposite of that, so it should be in the southward direction. If we look at our answer choice, or our answer choices, we can see that the correct answer is going to be answer choice C. This is question number 15. It says on a frictionless inclined plane, a mass with mass m slides down. What would be the normal force for the plane on the mass B? Okay, so since we're not really given anything, let's go ahead and draw out a picture to see what's going on. So we have an inclined plane that's frictionless and a mass m is sliding down. And we're asked to find the normal force that it's experiencing. So we know that the normal force is going to be perpendicular to the surface that it's on. So let's say that this angle is going to be theta. And we know that normally if the mass were on a flat surface, the normal force would just be equal to mass times gravity. However, we know that it's not a straight plane, but rather an inclined plane. So let's imagine what that would be. So if we were to try to figure out what this is, we can say that this right here is going to equal the normal force, which is equal to mg cosine theta. And if we were to rotate it clockwise, we would get something like that. And we would then see that the normal force would equal mg cosine theta. And so if we translate that into the actual diagram itself, we can see that the normal force, which is perpendicular to the surface that it's on, would then also equal mg cosine theta. And so if we look at our answer choices, we can see that the correct answer is going to be answer choice C. Okay, so this concludes our video of the Fall 2015 Simulated Exam 1. Please visit our website at uhscienceresource.squarespace.com for free video tutorials, practice problems, and videos of mock exams like this one. Good luck.